Hello everyone, welcome to Hacker Heap. In this video we will solve the problem count complete tree nodes. So what is a complete tree node? For a given binary tree, a node is a complete node if it has either one left child or a left child and a right child or no children at all. For this given tree there are 6 complete nodes, 1, 2, 3, 4, 5, 6, because even 3 had one left child and it doesn't have a right child, so it doesn't matter. But the criteria is it should have at least one left child and it cannot have 0 left childs and 1 right child. So in this tree the complete nodes are 1, 2, 3, 4 and 5. So this is not a complete node as it doesn't have a left child. So if you look into the Wikipedia definition, in a complete binary tree, every level except possibly the last is completely filled, and all nodes in the last level are as far left as possible. This is a complete binary tree, and if the node is on the right side, it's not a complete binary tree, and the particular node is not a complete binary node. So how do we solve this? So the easiest solution that was given by Leetcode or other people, which is accepted by Leetcode, is a recursive solution where we find the left and right height and just return with 1. If root is equal to null, all we are returning is return 0, or else return 1 plus count nodes of root dot left plus count nodes of root dot right. That's it. And if we submit it, it will be accepted. But there is a small issue with this. So if I give the binary tree, I have the tree visualizer. So the tree will look like this, which should fail. But the test case was not created by Leetcode. So if I run this code, what happens is, see, the output is still 6, but the expected is 5, even though I submitted all the test cases passed, but Leetcode didn't consider this test case. This actual solution won't work for this type of test case. So what we need to do is there is another solution where we can find a complete nodes using binary search. How do we do it? So for each level, the number of nodes will be 2 power 0 in the first node. At the level 0, it's 2 power 0. At level 1, it's 2 power 1. And at level 2, it's 2 power 2. So, but if the binary tree is not a complete binary tree, it's not a full binary tree. And if it's something like this, what we need to do is, we can find 2 power the depth minus 1. And we can find how many left leaf nodes are there, and we can count them as complete nodes. So let's look and see how we can achieve that. The first thing is we need to check if root is equal to null. We just return 0. And now we need to find the height or depth. Height is equal to find height of root. If height is equal to 0, we would return 1. Because at the 0th level, there will be one node, which is a complete node because it doesn't have both left and right. That is considered as a complete node. Now what we need to do? We need to find how many nodes are left in the last level. We know how many complete nodes are there except the level before the last level. So for that, we will use binary search. We'll start with index 1, and the right would be math.pow of 2 comma height minus 1. Let's change it to int. Now while left is then or equal to right, All we need to do is we need to perform the same old binary search. Int pivot is equal to left plus right minus left by 2. We will write a function if check node. We check if a node exists or not. We will pass the height, root, and the pivot. What we will do if there is exists, I will change the left is equal to pivot plus 1 like we do in binary search, and right is equal else right is equal to pivot minus 1. Once we are out of it, all we need to do is return math.pow of 2 comma height minus 1 plus the left. How many nodes are left? On the leftmost nodes on the last level, we need to change it to int. So that's it. Now let's go ahead and fill out these two methods to find the height, and int find height of pre-node root, int t is equal to 0 while root dot left not equal to null. All we are doing is root is equal to root dot left t plus plus return t. This will give us the height. Now we need to write one more function which will say if the node exists on the leftmost side. If check node of int height node root int pivot. We will perform the same thing like we did earlier. We will recursively call this check node using binary search. So we'll start with int left is equal to 0, right is equal to math dot pow of 2 comma height minus 1 convert to int. We will have one more pivot for this function. This pivot is like the basic starting index that we are considering. Now for the depth, for int I is equal to 0, I less than height, I plus plus, we will calculate the mid as similar to mid is equal to left plus right minus left by 2. That will get us the mid. If pivot less than or equal to mid, what we are doing is we are incrementing the root to root dot left and left is equal to pivot plus 1. Else what we do is root is equal to root dot right and right is equal to pivot minus 1. Alright, all we return is return root not equal to null, which will say if the leftmost node exists or not. Let's go ahead and submit. Okay, what we did wrong. Actually, we need to update the right here. Left pivot plus 1. Let's see. Okay, I know what's wrong. We need to assign the right to mid, not the pivot. This is basically the index. Yeah, it went through. So let's take a simple example and see how it works. And even this scenario will work for this. There you go, see. So the initial solution in Leetcode it works, but it's not the right solution because it doesn't work for this case. So we have to use this case where we are checking properly. So let's take a simple example and see how the code works. So let's take this tree 1, 2, 3, 6, 4, and 5. This is basically null. So we will find the height initially. So the height will be 2 at this point. Height is equal to 2. And then if height is equal to 0, we would return 1, which is not in this case. So we'll start with left is equal to 1, right is equal to L is equal to 1, right is equal to 2 power 2, 4 minus 1, 3 at this point. So we got the pivot. Pivot is equal to 1 plus 3 minus 1 by 2, which is 2. So pivot is equal to 2 at this point. We will check node passing this height, root, and pivot. So once we are here, we got the height 2, root 1, and pivot as 2. So we calculated again. Here the left changes to 0, right still is 2. We get the mid is equal to left plus right minus 2. At this point, it's mid is equal to 1. Pivot is less than or equal to mid, which is not. What we are doing is we are changing from the index from right to this, which is 3. So now root is equal to 3 and left is equal to mid plus 1, that is 2. Now we came here back and 2 plus 2 minus 2 by 2 is 0. So mid is equal to 2. And if pivot less than or equal to mid, which is true, pivot is 2 when we passed. So we go here, root is equal to root dot left, which is null. Now root is null. Remember, root is null. And we exit the loop. We are returning root not equal to null, which means it is false. We are returning false. So once it comes here, it's false. So we are updating pivot right is equal to pivot minus 1. So if you observe here, right is equal to pivot minus 1, that is 1. It will be 1. Now we go here, we check left plus 0. Now pivot is equal to 1. We will pass that. When it comes here, pivot is 1, root is 1, and height is still 2. Now we calculated, we start with 0, 0, and mid would be left plus right. It's still mid would be 2. Now we come here, pivot is 1 at this point, which is less than or equal to 2. So we go here, we change the root. Now root comes here and we change the right to mid. At this point is 2. So we come back and it's still the same. We will come back here. Now it's still the same. We come back here null and we will return true at this point, which will increase the pivot value to pivot plus 1, which in this scenario pivot is 1, 1 plus 1, which is 2. So left is equal to pivot plus 1, which is left. Now left will be changed to 2. Now once we exit out of the loop, what we calculated here is height is still 2, 4 minus 1 plus 2. That is 3 plus 2 equal to 5. That's what we want for this particular null case scenario. That's what we expected and it's there. I hope it's clear. Please do like and subscribe to the channel HackerCube. Thank you for watching.